Okay, here we go. We're supposed to rank moments of inertia here. I would start with looking at which one has the most. It's clearly going to be C because it has the most mass away from the axis of rotation. That's really what we're ranking. So this one has the most, almost all the mass, basically all the mass is away from the axis of rotation with this bit out here. Then we look at A and B, and if you mentally rotate A just around 90 degrees, rotate it this way clockwise, it's a mirror image of B. That's B, so those will be the same. So A should equal B. Already we can tell the answer is going to be, this is the only possibility. And then D is going to be the last. A and B are going to be bigger because we move the axis of rotation over here, so it has this much more mass away from the axis of rotation, whereas here we just have these amounts of mass. So that's going to be the ranking situation there. All right, here we're supposed to rank the net torque. So if we're looking from above, which one has the most torque? So the easiest way is to treat each T as just two separate pieces, each with mass M and length L, and then figure out how much torque combined. So for A, the net torque would be each one of those. So M1, so M1G would be the weight. That's going to be the weight of all of them. And its lever arm is L over 2. So it's this bit right here would have mg times L over 2, where the center of mass is, plus this little bit, which would be this mg, and its center of mass is at the same place there. So it would be the same, basically. Both of those would have the same torques that add up to mgl. You can tell probably just from looking that B is going to be the biggest. It has mg over L, right? That would be this bit right here. And then it has this mg over half the length there, right? So that would be 3/2 mgl if you combine the two torques on B. C is going to have an equal amount of torque and counter torque on either side, so it should add up to 0 down here. So it has the same amount of torque and counter torque on either side. And then if we look at D and E, I actually made a mistake on the key. Those are actually equal because if you think about it, looking at D, the torque on this little bit and this little bit will be equal and opposite because gravity will pull on each one equally hard, and they're torques and counter torques. So there'll be 0 net torque just due to this piece. So the total torque on D is just this piece, which would be mg times L over 2. This is what this little bit here alone is rotating about this axis. So this bit now creates 0 torque. So the only torque on E is this whole thing, which would be this mg, and its lever arm is L over 2. So those end up being equal if you look at it down here. So that should have been equal. So I need to correct that for those of you who put none of the above, I think on the test, that was the answer. Oops, not sure what happened there. Anyway, we want this to be in equilibrium, which means the net force has to be 0 and the net torque needs to be 0. So this is the only one that's satisfied. Let's pick. You can pick any axis of rotation. I picked this one. So if there's 10 newtons up in the y direction, there has to be 10 newtons down. So I need 5 newtons down somewhere, and to make the net torque equal to 0, to cancel out this torque, I need an equal and opposite torque applied over here. So that'll give me 5 newtons at the same lever arm in an opposite direction torque. So that gives me 0 net force and 0 net torque. Here we're supposed to rank the angular accelerations. So to rank angular accelerations, just set torque equal to torque. So force times lever arm equals I alpha, and just do that for each one. So if I solve this for alpha, alpha equals force times lever arm over moment of inertia. And here the length corresponds to the radius. So r is the same thing as the length, L. So that means F times L over 1/3 ml squared. I gave you the moment of inertia for this. The third doesn't matter because that will be constant. Since we're just ranking comparatively, I'm just going to drop the third out because that will be the same for everybody. So really it just comes down to alpha equals F over m over L. And so if you just put in the force of each one, so this, for example, A would be 2F for the force. The mass would be 2m, and L would be 2L. So it would just simply be 2F over 2m, 2L. So 2F over, so basically it's this divided by this. Here would be this divided by this. So this would be 4F divided by 4L times 4M. This would be 3F divided by L over M, and so on. And the only anomaly here is this guy right here. Since he's pushing at the axis of rotation, this actually would be 0 torque, which means this one came, I think, pretty close. We had to add in the D there, but none of the above are actually true because dead last has to be D, and that isn't true for any of them. And you could have saved a lot of time, actually, if you would have just seen that immediately. You could have made this a 2-second question. Okay. Here we're just supposed to solve for this mass in terms of the other things. So really you're just making torque equal to torque. I dropped out the G's because they'll cancel. This could be mg times L1, should be equal and opposite to big M1 L2, or big M1 G L2. G's on each side, they'll cancel. Do the same thing over here. Just set torque equal to counter torque. They should be equal and opposite. And now we just need to make a substitution so that M shows up. So you could do this a lot of different ways. Solve for anything other than M and you can get the right answer. I just chose to solve this one for L1. Solve for L1, and then I plug that in and substitute it in there. And then you do the math and you find that M equals the square root of M1, M2. Okay, power, what is the average power? Power is work over time, or it's force times velocity, or in rotational terms, it's torque times theta, but they're giving us omegas here, right? So what we remember here is work energy principle. Work done equals change in kinetic energy. Since they don't tell us about torque or theta or anything, we'll have to use the work energy principle. So I put change in kinetic energy up here, but it's rotational change in kinetic energy. So power equals change in final kinetic energy minus original kinetic energy. That is rotational kinetic energy. It's 1/2 I omega squared. We started originally with 0, so it really just reduces to power equals 1/2 I omega final squared over time. And then the half goes down to the bottom, and so this expression would be the right answer. All right, in this problem, we're just simply supposed to make an expression. This is a really good AP1 type question for, what is it, well, just basically a net torque equation. So the net torque is not M2G times R minus M1G times R. That's not right. It's just, if you're the pulley, the net torques are the torque due to T2 and T1. So the net torque is torque 2 minus torque 1. I made this direction positive, even though that's unconventional. You could switch it around and still be right. And then torque equals set net torque also equals I alpha, and that's really all it is. We just factor out the R, and so I alpha equals R times T2 minus T1, which is this. Basically the same thing as that. All right. Okay, on this problem, we've got a rolling problem. So potential energy here equals kinetic energy there. If it's frictionless, it just slides. So it's no different than a block sliding down frictionlessly. So it's just a gravitational potential at the top equals kinetic at the bottom. Solve for V. Boom, that's the answer, root 2 over G. But if it rolls without slipping, then we're going to set mgh equal to translational kinetic and rotational kinetic energy. So mgh equals 1/2 mv squared plus 1/2 I omega squared. But they don't let us have omega in the answer, so we need to convert omega into V. And omega is V over R, so V over R squared is the same thing as V squared over R squared. And then the rest of it is just algebraically solving for V. And there's the rest of the math there. So I factored out a 1/2 V squared, and then if you can just follow the math there, and that's this answer there, D. Number 10 is a conservation question. So this is the classic ice skater pulls her arms in, assuming it's frictionless with the skates. Angular momentum must be conserved, so it has to remain constant. So we know one of these two has to be correct because there's no net external torque on her. Kinetic energy is not necessarily conserved. You'd think it would be, but remember, when you pull your arms in, you're actually doing work, right? So number 10 would be, since she does positive work, applying force with her muscles in the direction of motion, her kinetic energy will increase as she spins faster. And so the positive work energy principle gives her more kinetic energy. All right, this last question is just a conceptual thing. The skater jumps on this board. Now it's not hinged here, which is kind of an important thing. So there's no, it's all frictionless under here. So basically we come in with certain momentum and we have to conserve that. So since there is no net external force and there is no net external torque, both have to be conserved. So linear and angular momentum are both conserved. Now, if this were hinged here, if this were a board that like had a hinge somehow here and still frictionless, that would introduce a net external force from the ground, right? If that were the case, it's another classic problem you see. Then the skater would jump on here, and then the answer would have been, some of you might have put this, linear momentum is converted to angular. That would be true, but because the linear momentum would not be conserved. So all the linear momentum would be converted to angular. Okay, on the first free response, some of you guys made this way more complicated than necessary, but they basically just wanted a linear acceleration A in terms of the quantities given here, which are m and r and things like that. So some of you did an I alpha torque equation and solve for A in those circumstances, and I actually accepted that, but it wasn't supposed to be all that complicated. It was just supposed to be a simple kinematic thing. So for that falling block then, x equals VOT plus half AT squared, just a simple kinematic equation will do. And it starts with zero velocity, kind of similar to a falling body, but the acceleration, of course, is not g. So just x equals half AT squared, and just solve that where x is d, and you get a equals 2d over t squared. That's all they really wanted there. So some of you did a lot more work than necessary. Then, graphing-wise, the next question is, what should you graph to determine the acceleration? So it's two different options. One is you could do distance as a function of time squared, right? If you solve this for distance, distance is proportional to time squared. So that would give you sort of like a linearization. That would give you a straightened curve, not distance versus time values, but distance versus time squared. So you could do distance times squared values and find the slope of that, and that would give you an acceleration. Or many of you said, well, I want to plot v versus t. They didn't give me velocity values, but given the distance values, you could determine that. The common mistake there, I think, was if you took the average velocities for those seconds, they came out, so if you did distance over time average, you got those. But remember, those were the average for those seconds. So you need to find the instantaneous speed or velocity at the end of the first second, which would be twice the average. So if you double the averages, you get the instantaneous after each one of those seconds. And so here's this second, this second, this second, this second. You double the average during the second to get the instantaneous at the end of each second. And then if you graph that, you'll get the correct answer as well. You would get, I think it came out to close to 2. Yeah, I did it both ways and got right at just a hair over. I got exactly 2.04 if you find the slope that way. All right. The next part of the problem says find the I value of this pulley. They're not telling you it's just a cylinder, so you're going to find some expression using all these variables. So really all we want to do is find a net force equation on M and a net torque equation on the pulley. So let's make this direction positive. The net force on him is going to be mg down minus the tension in this up. And the net torque around him will be the tension in this times R, that's the force of tension times the lever arm, and that will equal the I alpha, which is also torque of the whole cylinder. And those are the two equations we're basically going to use to solve for I. So that's done right here. So here's where net force is mg minus t, net torque is that tension times lever arm equals I alpha. You can solve this several ways. Here you just solve for alpha equals A over R. And so you can solve for I there, and then you can plug it in later here. So then this equation is solved for t equals m times g minus a, and then we're just doing some substitution and some simplification. Some of you wrote something like this or this. There's several different ways to express that, so several different versions of this is correct. The last question is a conceptual question, and it says the pulley was taken off and they measured the rotational inertia. It was bigger than measured, right? So if it's bigger than measured, that means what we measured was a faster acceleration that would correspond to a smaller I value, but the actual was larger. So you can't say friction was the cause of that, because friction would have made it gone the other way, right? Friction would have made the measured value a bigger moment of inertia, and then we would have taken it off and found that, oh yeah, it was smaller. So it'd have to be something else. So two different possibilities. One is, the rope could wrap around here and layer on top of itself, which would create more torque, right? That could explain it, because that would actually give it a greater torque and cause our measurements to have been smaller. The other option is the other possibility would have been there was some slippage. If the rope is slipping as it comes out, that would cause us to measure a greater acceleration than really should have been, and that would account for the fact that the rotational inertia ended up being bigger. I suppose there's some other things that could have been going on, but friction is not one of the answers. Finally, this last free response, we're supposed to state why N1 plus N2, which are the normal forces of the two hinges here, the little support beams or whatever you want to call them, what are they? And that's just a very simple thing, because if you just look at this as before we even think about rotational motion, we know the net force in the y direction has to be 0. So the weight of the guy plus the weight of the beam has to be equal to the weight of N2 and N1 combined, and that's all that was simply asking. So N1 plus N2 up minus the weight of the person and the beam, it's got all that up to 0. Simply means that the two weights down must equal the sum of the two supports up, which turned out to be 882 newtons. And then finally they want to know, all right, so you start walking here, when does it teeter? Well, what happens right when you walk out here and it teeters, this goes to 0, so this becomes a really simple torque problem. If this is out of the way, all we're doing is we're rotating about an axis right here. So then the weight of the beam is equaled whenever I get a certain distance out by my weight out here. So my torque plus the beam's torque's got to add up to 0 right at the moment when it starts teetering. And the second I go any further over, the whole thing will topple over. So you just set those two torques equal to each other, and you can solve for R, but that's the point from the hinge, and I only counted off a point. They actually want the point from the end, because that's what you might want to know. How far from the end can I get here safely? So this distance is, the distance from the hinge would be 1 meter.